about it. All right, guys, let's continue about 26. Now, keep in mind with chapter 26, it is all a big change now, and we're now discussing the urinary system. So let's take a look at that picture. Obviously, they're doing some kind of kidney transplant. The kidneys themselves, when you take a look at a picture of it, they do kind of look like kidney beans, right? And the main thing that we're going to discuss is, and keep in mind, overriding picture, just like we talked about with overriding picture of our, our overriding picture of our, when we started discussing the metabolism and chapter 24, is that you don't know when your next meal is coming. So you want to be able to efficiently digest and absorb as much nutrients as you can. Same thing, but even at a higher level in terms of water. We didn't know when your next drink of water was coming. Because of that, you need to be able to filter, reabsorb as much water as you can. Not only that, salts, right? Sodium chloride is incredibly important. Now we think of it as like a nuisance, right? Everything has salt in it. So we get too much salt, even untasted salt. The problem is now it's so, ubiquitous, but about 100 years ago, it really wasn't. Sodium chloride was hard to get. You guys have heard of people saying that somebody is worth their weight in gold. Well, back even before gold became popular, was they're worth their weight in salt. You've heard of like Roman garrisons being paid some of their wages in salt. Why? Is because salt is something your body needs. Gold is something we want, but salt is something we need. So if you don't get enough of the salt, we will have some major issues related to water balance. And that's for just sodium chloride. You can imagine what would happen if we're talking about potassium chloride. That's even more important type of salt. So salt is incredibly important. We want to filter and absorb as much of it as we can. But all right, we don't want to just release it out in terms of urine. So in terms of the functions of the urinary system, we need to filter blood, and because of that, we need filtration, and then we need to reabsorb as much as we can. 99% reabsorption, it can get up to 99.9% reabsorption of water. And then secretion of certain things we want to get rid of, like urea, right? Urea is toxic. All that nitrogenous groups are toxic. So we need to secrete some of it. So then we can get rid of it. Because of its ability to filter, reabsorb, and secrete, it plays a big role in our blood volume, right? Kidneys do a great job for volume overload. So when you have too much liquids, your body and your liver does a great job getting rid of it. It doesn't do a great job when you're dehydrated. It can't make brand new water, in other words. It kind of makes sense, right? That's why we get thirsty. Now we'll talk about why you have that sensation when it's summertime, you're out in the yard, or you don't even have to be moving, but it's so hot and you're just sitting out in the sun. Sometimes somebody offers you like a soda, doesn't even taste good, not even appealing. All you want is cool water, right? There's a reason for that, and we'll talk about why coming up. But keep in mind, kidneys, great when you have too much water, as long as you let yourself urinate. Obviously, right, you guys have all heard the stories, especially if you're in my class last semester, heard the story about the Nintendo Wii situation and how people will sometimes do kind of stupid things without thinking about it, which is drink as much as they can and hold their urine for some reason. As long as you let yourself urinate, your body can get rid of massive amounts of blood volume and water volume. Regulates concentration of sodium, potassium chloride, calcium, and phosphates. It also regulates pH, right? Secreting hydrogen in the urine. And remember, when we secrete hydrogen into the urinary system, into the urine, that means we have less hydrogen in the bloodstream. This is going to be one of the main reasons why our blood pH is slightly basic. It's not neutral. And this one that most people don't think about. Erythropoietin, EPO, is produced in the kidneys. And it's going to be released from the kidneys to stimulate red blood cell production. So if you've ever seen somebody that, even in movies, that are in chronic or acute renal failure, the kidneys have failed, they look almost green. The reason why is because the lack of EPO, they don't have as many red blood cells as they should, and they don't have, right, the ability to, kind of dilute and concentrate urine. But the weird look is because of that lack of RBCs. All right, so let's continue here. And keep in mind, and I do have videos online about where the kidneys are, histology. And on Thursday, tomorrow, I will actually go through the anatomy and physiology revealed and still talk a little bit about the kidneys there. And I'll show you the pancreas and everything else. All right, I don't know, somebody, okay. So let's talk about this. Location of the kidneys lies behind the peritoneum, and because of it, we call it retroperitoneum. The peritoneum is going to be that kind of serous connective tissue, and it covers the lining of your stomach, your abdomen, I mean. So in your abdomen, think about, you have the rectus abdominis, the internal and external obliques, and then the deepest muscle layer is your transverse abdominis. Well, on the inside of your transverse abdominis, facing where your internal organs are, your stomach, your large and small intestine, in that internal lining of the transverse abdominis, we have peritoneum, connective tissue. We call that the parietal peritoneum. And then in the, GI tract, right, areas of the abdomen, they're going to have also connective tissue in the small intestine parts, all of the large intestine, your stomach, all have a little bit of also connective tissue that we call the visceral peritoneum. Now keep in mind, we saw something similar in the chest. In the thoracic cavity, we had parietal pleura that was adherent to the inside of the ribs. That parietal pleura, and I kind of mentioned it previously, in the ribs, the parietal pleura, there goes my dog going crazy, sorry. The parietal pleura is going to be lining the inside of the ribs, all right, and it forms a seal between the ribs. That's also that connective tissue that we see when we're cooking ribs that we have to remove from the inside, right? That parietal pleura is like the parietal peritoneum. The visceral pleura is found on the lung itself. Same thing here. The visceral peritoneum is not just found on one organ though, right? Here, the visceral peritoneum are found on all of the organs that are found in your abdominal cavity. So your stomach, found in the abdominal cavity, it's gonna have visceral peritoneum. Your small intestines, parts of it, of the duodenum are retro, but a lot of the duodenum jejunum are all in the peritoneum, intraperitoneal, and it also has visceral peritoneum. And then your large intestine throughout the whole length is going to have visceral peritoneum, right? That peritoneum makes it so then it has nice sliding effect when and if it touches the parietal peritoneum. It also tells us, and it orders where the organs are. So when we say something is retroperitoneal, we're saying it's very far back, posterior abdominal wall, and it's so far back that it's on the sides, right, on either side of the vertebral column. So it is at the same depth as the lumbar vertebrae and the body of the lumbar vertebrae, which is crazy. It's very far back. The right kidney is slightly lower than the left. In terms of the external anatomy, the renal capsule is like the pia mater. It encapsulates the whole kidney right here. So when you take a look at this picture, the renal capsule is this like external shell, external tissue covering the whole kidney. You can't remove the renal capsule without damaging the kidney. the pararenal fat engulfs the renal capsule, so it covers the renal capsule. And keep in mind that, right, unlike the rest of the, you know, unlike, let's say, the lungs and the heart, right, where it's all kind of protected by ribs, kind of protected by the vertebrae, well, the kidneys are somewhat protected. Some of the protection, especially for the left kidney, is a little bit higher up. Well, some of the kidney is going to be so high up that it's protected by the rib cage, right? Now, the last little bit that comes down here, that's not protected by the rib cage, but it's going to have a little bit of pararenal fat that protects it, right? So the hilum here is where, like the hilum of the lungs, where all the arteries, veins, and nerves enters and exits. The hilum opens into the renal sinus, which is empty cavity filled with fat, loose connective tissue, and fat and loose connective tissue. Now, keep in mind when we're talking about the kidney itself over here looks like a kidney bean and is going to be divided into an external region called the cortex. The internal region is called the medulla. The medulla is divided into what looks like little bulbs or pyramids. So when we see the renal pyramid and we see medulla, what's the difference? The medulla means the whole internal aspect of the kidney. The medulla is divided into functional regions that we call the renal pyramids, right here. So the renal pyramids are the functional areas of the kidney. Now, what else do we see in the medulla besides the pyramids? We have spaces that are absent of the pyramidal region right here that looks like empty space right here. That's where the blood vessels are. This is called the renal column. So the renal column and the renal pyramids combine to form the renal medulla. So the renal pyramid is a component of the renal medulla. So eventually, I want you to understand this, and probably the easiest to understand is that the functional cells, the nephron, right, is basically a series of funnels. That allows you to filter and reabsorb and then bring any excess amount of fluid out, so then we can bring it into ever-larging funnels, eventually draining out into our ureter, which is the largest funnel. The apex of the pyramid empties out into a renal papilla, and think of the renal papilla as like a shower drain. A shower drain has openings for that fluid to go through. That's what the renal papilla is a drainage area for all unabsorbed fluid to then pass through and then gets funneled out into the ureter. By the time fluid goes into the renal papilla right here, or papilla, right, as it goes in, right, that fluid now cannot get reabsorbed. At that point, it turns into urine. So the renal papilla then empties into minor calyces or calyx. Several minor calyx empties into a major calyx. Here's one major one, here's another major one. Several major calyces then empty into renal pelvis. The renal pelvis exits the kidney and drains through the ureter, right? So the pelvis will turn into the ureter. It's a continuation of the ureter. I mean, the pelvis is a continuation and leads up to the ureter. The ureter then descends and empties into the bladder, right? So again, once things get through the drain, the renal papilla, any filtrate, any water, any salts, even glucose, right? Once it goes through that renal papilla, there's no reabsorption possible, right? Then we call it urine. So there's a distinct time when we call that fluid urine. Once in the pyramids, we don't call it urine yet. Instead, we give it the word filtrate. Once it passes through, though, it turns into urine. Right. So let's look at the pyramid and take a look what's inside of the pyramid that makes it so important. right? So the functional, so here's one pyramid right here. And with the renal pyramids, right, we're gonna see on a microscope the actual collection of cells that gives the kidney its function, right? It's not just one cell, it's a collection of cells that make up the nephron. Keep in mind, when we are looking at the nephron, right, when you have kidney failure, when you have issues with the kidney, you don't go see a kidney specialist, right? Or you see a nephrologist. Why? Because a nephron is a functional clusters of cells that forms the capacity to concentrate and to get rid of fluids in the kidney. So the nephron is all of this, is a combination of what we call the renal corpuscle, right? And a collection of cells that make up the proximal convoluted tubule, the loop of Henle, descending limb, ascending limb, then the distal convoluted tubule, and then the collecting duct, right? The whole thing is part of our nephron system, meant to filter, reabsorb, secrete, and then eventually excrete any excess amount of water, salts, and even sometimes glucose and amino acids. Now, most of us, we should not see glucose in our urine. We shouldn't see proteins in our urine, and we'll talk about why in a few minutes. Again, everything starts with blood going through this kind of bulby area called the renal corpuscle. We're going to see the renal corpuscle is a collection of two different distinct components. The renal corpuscle leads into the proximal convoluted tubule, which leads into the descending limb of the loop of Henle, or glomerular loop, which then leads to the ascending limb, which then goes to the distal convoluted tubule. Many distal convoluted tubules then drain into a collecting duct, which then brings that fluid, that filtrate, through that drain of the renal papilla. Once it goes into that drain, no reabsorption will occur, right? So anything after this, that's going to be the minor calyx. We're going to see in terms of nephrons, right? Some nephrons are going to have most of its whole length close to the cortex. So here's a cortex right here. We call those nephrons cortical nephrons. The loops here don't extend deep into the renal pyramid or the medulla at all. And we're going to see, right, the greater the length of the loop, the greater the ability to absorb water and to concentrate urine. So here you can imagine it's important for reabsorption of nutrients, but it's not quite as important, these cortical nephrons, in terms of concentrating urine and for water reabsorption, right? The ones that are important are the juxtamedullary nephrons. The juxtamedullary nephrons have its start, the corpuscle, next to the junction between the cortex and the medulla. That's why we get the word juxtamedullary, right? Then they have very long loops, nephron loops, or loops of Henle, right? Keep in mind, it starts here at the renal corpuscle, then goes to the proximal, and then the descending limb, then a U-turn to the ascending limb. The loop of Henle extends deep into the medulla. This long loop extending deep in the medulla gives us the ability to concentrate urine. And by concentrating urine, we're reabsorbing a lot of fluids. So then we have greater ability to reabsorb water and salts, right? And later on, some of you guys might have heard of loop diuretics before, right? And loop diuretics, we're gonna see, like hydrochlorothiazide. Well, those loop diuretics work on these loops that we're talking about here. And we'll talk about why that causes you to urinate so much, because that's what diuretics do, right? So we'll talk about the actual mechanism behind those later on. Now, let's talk about the first part, the renal corpuscle. Take a look at this. You first have a series of arteries, the afferent arteriole, that brings blood under higher pressure into our network of capillaries called the glomerulus. So when we talk about the renal corpuscle, it's not just one thing. It's actually two separate components. The first component is the actual blood vessel that we will filter. And remember what filtration is. Filtration, kind of like our vacuum cleaner, right? In a vacuum cleaner, we're taking air, dirty air from our carpet, and then we suck up that dirt, right, from the carpet, and then we push it through what looks like foam pieces and some filtering medium, right? What happens? Well, the foam and the filtering medium contain small holes. So air gets right through because it's small, but dirt's a pretty big piece, can't get through those microscopic openings in the foam. So it gets trapped on the foam because it can't get through, it's too big. What happens then? Well, your foam starts getting dirtier and dirtier the more you use the vacuum cleaner. And that's what it's supposed to do. It's supposed to trap those large dirt and hair particles. So then what exits on the other side is free of dirt and hair, and it's just clean air. That's filtration in terms of our vacuum cleaner. We're going to see something very similar in our body, right? Instead of air pressure, what do we have? Blood pressure. Blood pressure, then, whoops, I kind of moved that. Blood pressure is going to take blood from the afferent arteriole and force it into the glomerulus. And we're going to see the glomerulus are just nothing more than capillaries that are fenestrated. In other words, it's got slightly larger gaps, right? And if we just had those fenestrated capillaries, proteins can get through. That's not good. So we don't want those fenestrated capillaries to allow proteins to get through. That's where the Bowmans capsule comes in. The Bowmans capsule has two components. One forms our first microscopic funnel. It's this external region right here. This external region is called the outer parietal region. And the main thing about this is that it forms that funnel to catch any fluids, any amino acids, any small proteins, any glucose and ions that we push through our filtering medium. All right, so again, parietal catches any of the fluid that we filtered, catches any of the ions and molecules that we've filtered out. To stop large and medium proteins from getting through, we have a visceral layer that covers the glomerulus. The visceral layer contains specialized cells that we call podocytes. Those cells, very similar to astrocytes, right? In astrocytes, like we talked about last semester, astrocytes covers your blood vessels, preventing things from getting through. It helps form the blood-brain barrier. Well, we don't need anything quite as tight here, right? We need a little filtration. We need things to get through. We just want to stop big things from getting through. Podocytes wrap themselves around the openings of the blood vessels, those fenestra, covers them up, so then small things get through. Water gets through. Glucose now gets through. Small proteins can get through. Amino acids can get through. Salts can get through. But that's about it. Medium-sized proteins, large proteins like albumins, they definitively can't get through. Red blood cells cannot get through. That's why you should never see red blood cells in your urine. That's why you should never see albumins and proteins in your urine. That's why you should never see white blood cells in the urine. When you see any of those components in your urine, that means that something is very wrong way up here, or something's very wrong in your bladder, right? Some kind of infection, right? Why? Because we have protection. We have a filtering medium, the podocytes, covering any gaps, right? And you have the fenestra. Remember, fenestra in chapter 21. Fenestra are windows that are found between our endothelial cells that allow small, medium proteins to get through. Well, we don't want, small and even medium proteins to get through. So we need to cover up those windows. That's a function of podocytes. Eventually, we force that fluid out. The fluid then goes into the very start of our nephron loop, right? Nephron system, which is a proximal convoluted tubule. Well, what would happen if I pump out a lot of water here? If I lose water, that means the blood that exits should have less water, right? Because it's going into the loop, right? It's going into the nephron. That's why on almost every picture you see of the corpuscle, on almost every picture we see, we notice that the afferent arteriole, look at how big it looks compared to the efferent. Efferent is the exiting arteriole. The exiting arteriole then comes out, and because it's got less blood pressure, because it has less water, it almost always looks smaller on a diagram. And it's a sign that, yeah, the fluid that comes out, well, that's been filtered, you've lost a lot of the water, the arteriole is smaller. Again, the fluid is now being pushed into the start of our reabsorptive system. So here is our Bowmans capsule again. And keep in mind, take a look at these tiny cells right here, kind of covering the afferent arteriole, bringing fresh blood in. Those cells are incredibly important, right? Because the last thing we want to do is this. What happens after you have you've had a huge drink of water, you've been thirsty, right? And usually it happens in the middle of the night, you wake up and you're thirsty, so you drink almost a whole bottle of water. Well, what happens is our body does a great job getting rid of excess blood volume. So you pee out more watery urine. But do we want to keep peeing out watery urine? In other words, what would happen if I drink water, start urinating, and keep on urinating watery urine? Eventually I'll be dehydrated, right? So I need a negative feedback system that allows me to get rid of any excess water. At the same time, we need to stop urinating that excess water when we have gotten rid of our concentration that is over the top, right? So we need a negative feedback system to make sure that because we drink water, we can urinate out any excess, but we want to make sure that we don't become dehydrated from urinating all that excess water. So this is our negative feedback loop right here, right? We're going to see this system between the juxtaglomerular cells lining the afferent arterioles and specialized cells found as part of our distal convoluted tubule. Take a look at this right here. You can see the distal convoluted tubule always wraps around, right? And we're going to see later on that, see how the distal, so here's a proximal convoluted tubule. It goes through the descending limb, makes a U-turn to the ascending limb. So this part right here, the distal convoluted tubule, somehow makes its way back around, so it makes contact with the afferent arteriole. In other words, it doesn't go over here. It goes back so then it can make contact with the blood vessel. Why is that part important? Because, right, these are going to be our negative feedback system. In the distal convoluted tubule, we see specialized cells called the cells of the macula densa. Those cells will notice any large increase in filtrate speed and volume. Right? The filtrate is what we call that fluid after we have filtered it and before it becomes urine. So as the fluid goes down this whole system in our nephron, right? As it goes into the descending, ascending limb, into the distal convoluted tubule, into the collecting duct, we call that fluid filtrate. It's only when it goes into the renal papilla that it becomes urine. Until then, we call it filtrate. And what we're going to do with that filtrate is to have a negative feedback system here. So then the distal convoluted tubule and their macula densa cells will sense a big increase in amount of filtrate going through. As there's a big increase in amount of filtrate, it's going to cause a negative feedback loop here. So then I don't pee out any excess water beyond what I have drinking out, right? So you want to have a negative feedback loop, right? So when you drink that gallon of water, I mean, you guys probably seen people working out. Hopefully we still can work out once it's over, right? In the gym. And you see that, you'll always see that one obnoxious person that's carrying like a big old gallon or, jug of water. And like, really? You need that much water, right? So what happens if you would drink that whole gallon of water? We have volume excess. We have volume overload. What happened is it has a slight increase in blood pressure here, which forces excess fluid in your blood to be pushed out. As it gets pushed out, well, that's good because we're going to see the more we filter here, the more urine you will excrete. But there's a time and frame where we excrete that excess water, but if we excrete too much water, we become dehydrated. And we should not get dehydrated from drinking water. The macula densa and its action with our juxtaglomerular cells prevent that from happening. This is a system of negative feedback. The macula densa cells senses increase in filtrate volume and filtrate speed. It senses increase in sodium, right, volume and speed going through, and it causes these cells, we call juxtaglomerular cells, to pinch the blood vessel. As we pinch the afferent blood vessel, less blood gets through. Less blood gets through, less filtration. That way we limit how much water we can get rid of. This is our negative feedback system, right? The more we filter, the more goes through our loops. The more that goes through our distal convoluted tubule. It's sensed by the macula densa cells. The macula densa cells then starts pinching off that afferent blood vessel. As that pinches off, there's less water that gets filtered, or less blood that goes in, less blood going in, less filtration. That's our negative feedback loop, to make sure we don't pee out any excess water beyond what we're drinking in. So then we're not dehydrated when we drink a lot of water, because that shouldn't make sense, right? We shouldn't get dehydrated when we drink water. But if we keep producing watery urine, right, then we will become dehydrated. So we need a negative feedback system. This is part of our negative feedback system. And we'll talk more about it on Thursday. Now, the filtration membrane is how we filter the blood and limit what gets through, right? Keep in mind that we have fenestrated capillaries here with tiny, I wouldn't say tiny, but medium-sized gaps within and between our endothelial cells that make up our glomerular capillary, right? So the glomerulus is just a weird looking modified capillary bed, right? That looks like a cauliflower. Now, it's fenestrated because it allows more fluid to come out easily. The problem is because of the fenestra, proteins, small and medium proteins can get through. Still, large proteins can't, and whole cells can't. But medium-sized proteins can. So we need to stop those proteins from getting through. That's where we have our podocytes. Our podocytes are like our astrocytes. It basically covers the entirety of the glomerulus. So here's one podocyte, here's another one. Each podocyte covers parts of the glomerulus. As it covers it up, it has interdigitated fingers. Kind of your fingers, when you put it one next to each other, right? Like you're clasping your hand. Well, we call that interdigitating, right? So one part goes up and down like digits. And what it does is it completely closes off our fenestra. So then instead of these large openings, we have small, narrow slits, and that's it. Blood pressure forces then that blood into this area, and water can exit out. As water exits out of those slits, where does it go? Right into, our funnel, our Bowmans capsule right here, where then we can funnel it to the start of our nephron, our proximal convoluted tubule. So these slits are going to be important in stopping small and medium-sized proteins from getting through. The basement membrane, sandwiched between the endothelial cells of the glomerular capillaries and the podocytes, also acts to stop proteins from entering. So now we have stopped proteins. Only thing that can get through, glucose, maybe some amino acids and peptides can get through. Some, a lot of some urea gets through, and glucose, salts, and water. Salts and water get in and out easily. We call the combination of the endothelial cell, the little slits that we form by the podocytes, and the basement membrane of the cells, the filtration membrane. The filtration membrane is like our foam that we see in our HEPA filter. That filtration membrane is going to allow water to get through, salts to get in and out really easily, but larger particles have a harder time because the gaps between these cells now are too small. Again, there's a reason why we should never see big proteins in our urine, because if the system is healthy, large proteins should not get out. It should be blocked by all this. Medium-sized proteins should be blocked, and even smaller proteins could be blocked. Definitely whole cells shouldn't get through. That's why you should never see any of that in our urine. Again, this kind of goes through the glomerulus and the circulation. Afferent brings it in to be filtered. Blood pressure increases filtration. Efferent drains. We're going to see, as soon as a little bit of fluid comes out, some of the fluid comes back in, Not all of what we filtered goes into the proximal convoluted tubule. Some of it will start to also almost immediately go back into the glomerulus. Eventually, though, there will be more filtration than reabsorption. The juxtaglomerular apparatus, site of renin production. We'll talk about renin later. Also, there's a big one, site of our negative feedback system right here. Prevents excessive urine production and is a combination of juxtaglomerular cells that are embedded on the afferent arteriole and macula densa cells from our distal convoluted tubules. These cells senses increase in filtrate speed, increase in filtrate osmolarity. Then it causes these cells to constrict the afferent arteriole. The smaller the afferent arteriole, the less blood goes into the glomerulus. You can't filter what's not there. If there's very little blood going in, there's not much filtration. So you're going to decrease filtration, decrease urine output. It's our negative feedback system. Now, I will stop right here for today.